This is Hacker Public Radio episode 3309 for Thursday, the 8th of April 2021. Today's show is entitled Linux Inlaws S01E27, The Big Uncertainties in Life and Beyond. It is hosted by Monochromic and is about 57 minutes long and carries an explicit flag. The summary is, the two chaps discuss uncertainties and beyond in this episode on probabilistic data structure.
This episode of HPR is brought to you by anhonesthost.com. Get 15% discount on all shared hosting with the offer code HPR15. That's HPR15. Better web hosting that's honest and fair at anhonesthost.com.
This is Linux Inlaws, a podcast on topics around free and open source software, any associated contraband, communism, the revolution in general, and whatever else fancies your tickle. Please note that this and other episodes may contain strong language, offensive humor, and other certainly not politically correct language. You have been warned. Our parents insisted on this disclaimer. Happy, Mum? Thus, the content is not suitable for consumption in the workplace, especially when played back on a speaker in an open plan office or similar environments. Any minors under the age of 35, or any pets, including fluffy little killer bunnies, your trusted guide dog, unless on speed, and cute T-Rexes or other associated dinosaurs. Welcome to Linux Inlaws. Season 1, episode, I can't even remember, Martin, what episode is it?
Episode where Jitsi vaguely works.
Maybe it's episode 40-something, which is, of course, a segue to today's subject, namely probabilistic data structures.
Take
And
300.
Yes, and for this subject, we have no other than our beloved Elena. You probably remember her from the peasant girl role, back in the Halloween special of something called Linux Inlaws. If you haven't listened to it, dear listenership, please go back. You'll find the link on the website. An episode not to be missed, apparently, I understand. Yes, exactly. So when Elena is not working as a voice double, she's actually working at a company called Redis. But maybe Olga/Elena, why don't you introduce yourself properly?
Well, you already know Olga, so I'm just gonna summon my Elena persona.
Please do, yes.
Okay.
Any else we should be aware of here?
No. That's me. My Elena persona is pretty stable. Although I have different roles. I have my professional role, of course. I have a role of a mom. I have a role of a friend. But in this context, let's talk about the professional Elena. So I work for Redis Labs as a technical enablement. Now senior technical enablement architect.
Well done, by the way. Before I forget this.
Thank you very much. Technical enablement architect basically means we help the technical field, everyone in the field in technical roles, to first of all get up to speed with the system with all our architecture when they join the company, and then also maintain their knowledge fresh by releasing new trainings about all different technical aspects of our system. So that's what I do professionally. Outside of that, I think that's really close to my heart is the women in tech question. But I'm personally, I'm more of the type of women who, instead of going on Twitter and complaining about what someone did, I like to roll up my sleeves and get some work done and do some coding or just become a better engineer in order to be a stronger woman in tech, woman in technology. So I had done some work previously on that field, and a while ago I was invited from the Women in Tech Global Organization to be the global global education program director. So now we're working on that. We have some partnerships with Cisco, Microsoft, and we're going to be doing some free courses for women and people who identify as female or minority in technology.
Wow.
So yeah, coding
That's
and
impressive.
That's my thing.
Excellent. Okay. Full disclosure, people. First, I really met Elena. I think it was in December 2019 in London, when you gave a presentation on something called probabilistic data structures for an in-memory NoSQL database called Redis.
Yes.
And this would be today's subject, as in what are really probabilistic data structures and why are they important? Not just in a Redis context, but generally speaking. But before we go into these technical details, maybe it's worth explaining what Redis is in an in-memory NoSQL context, given the fact that 2/3 of today's speakers on this podcast will still work for Redis. One defected quite some time ago. So let's do this jointly. Redis is about 10 years old. It has the spot, I think it has the 7th rank on a website called DB Engines, if I'm not completely mistaken. And if Stack Overflow is anything to go by, it's the most loved database for, I think, at least 4 years in a row, as in terms of voted for. The main differentiation, it's probably the best term, what I'm looking for, is actually that in contrast to other databases, Redis does it all in main memory in terms of yes, it supports persistence, but the main focus of the processing of data is actually doing this in main memory, and hence this kind of playground of real-time performance. But why should I do all the explaining? Elena, Martin, feel free to chime in.
Well, you started really well. Redis is very fast. It's very loved by developers, and I can talk about myself. At least one of the things I loved that made me fall in love in Redis even before I knew about Redis Labs. So before I joined Redis Labs, was the efficiency and the part that it doesn't necessarily stick to all of the academic dogma. It just uses just some approximations to get things done and make them work very well in 99% of the cases for people. Okay. So since this is a episode of probabilistic data structures, even in Redis itself, we have a lot of approximations. Like if we talk about the LFU, LRU, the eviction policies in Redis, they use approximations too. And I kind of like that efficiency, being very small memory footprint, very fast. It does things well and fast.
Martin, anything to add?
Yeah, I think the one thing I think for people not familiar with Redis is that it's basically a bunch of data structures that you use for different purposes, right? Which as opposed to your relational database, which has tables and those kind of structures, it's a bunch of different data structures which are very close to programming paradigms instead. So it's more of a builder's type of piece of technology, right?
Interesting observation there. Yes.
Bunch of Legos for us to play with.
Lego, yeah.
That's actually very good image there. Okay, but enough about Redis details. Elena, what exactly are probabilistic data structures, and why are they so important?
Okay, so what exactly are probabilistic data structure? It's a group of data structures that give a reasonable approximation of an answer, but using just the fraction of the usual time and the memory that the deterministic data structure would use. So they use hash functions usually to randomize and compactly represent a set of items, and then collisions are ignored, which usually leads to some margin of error.
Before we go any further, I think we cannot assume that everybody knows what hash functions are and what collisions are.
So hash functions is a way. Okay, how do? So let's say you get a value. You hash it. I don't know how deep should we go into explaining how hash functions work, but you hash that value, and many different values can have the same hash, and that would be then a hash collision. I like to use this analogy. If we have people that don't know what's a hash function, then I like to use this analogy. If the object that we have is, let's say, the real life object, a hash of that is its shadow. Okay, so the shadow of that object would be its hash. It kind of is a silhouette of what was there. You can kind of tell something about it, but you cannot know what is it. And many different objects, let's say a ball, someone's head, or a lamp can have the same shape of a shadow. But in fact, they're different objects.
Very much so. I like the image. I like the comparison there. I like the analogy. Let's put it this way. Beautiful.
Thank you. In probabilistic data structures, you use that kind of, you represent the elements with their shadows, basically. Now,
by the way, before I forget, very practical uses of hashes are actually if you log into a Linux/Unix system, because the passwords stored in etc passwd or in etc shadow are actually salted hashes. I won't go into the technical details, but this is the primary touch point if you use a Linux-based system. When you log in, type in your password. The password is not stored in clear text in etc passwd or in etc shadow, but rather as a hash.
So nothing to do with the probabilistic data structures here. No, you don't.
Thank you, Martin. So let's cut this short. And this is just another application of a hash. So the idea is basically you enter a password. This password is then converted by a hash function to a hash, and then the hashes are compared. Should these hashes match? Essentially.
Exactly.
Sorry, but I didn't. Yeah. Back to you, Elena.
But it's still connected. Nothing to do with probabilistic data structures, but they use a deterministic function. A deterministic hash function means that every time you run it with the same input, it's going to give you the same result, the same output. So actually, I'm not sure if that is true for passwords, to be honest. I guess depend on the system. It should be, at least. But for PDS, can I use PDS? Probabilistic data structure.
Thank you. Yes.
It is definitely true and crucial to their functioning. Now, why would someone use probabilistic data structures? You would ask, okay, well, why would I want to sacrifice precision? Right? We are developers. We work with exact thing. It's an exact science. I want to have my results always correct. But there are cases where you would sacrifice some precision, some accuracy, if you can gain space or time. So there is this thing called this triangle. The triangle of space-time accuracy in data processing, where you have space, accuracy, and time and component on the three edges of the triangle, and you can choose two. You cannot have three with the data structure. So it's either you're going to have accuracy and low memory, but then you sacrifice time, and so you don't get real-time results, or you have space and time. In the case of probabilistic data structures, you save on space, You have good time performance, but you sacrifice accuracy. You cannot have all three. Just
This
like
is also,
in the cat theory.
Exactly. This is also known as the Kolafska Theory, right? If I'm not completely mistaken.
No, I don't think so.
Maybe I'm wrong. I don't know, but
maybe there was some Kolafska who lived long before me. Some mysterious. There is this mysterious people in the PDS world, but we can talk about that. The Bloom guy, one of the most famous structures.
yes.
Dr. Bloom, he's completely mysterious. You can't find anything about him online. You can no photos. We don't know if he's still alive or not. He's mysterious.
Yes, let's park this for about 2.5 minutes before we go into the subject. But okay, Martin, any thoughts on PDSs before we move on?
Well, we're not moving off PDSs, are we?
In terms of the principles and stuff and whatever, the theory that is.
Yeah, no, that's very well put about the trade-offs, right? It's a very different approach in terms of if you look at it from different databases or different technologies, you're effectively at storage time. You compute a data structure rather than just storing all the data as is and then calculating a result out of those, which of course.
I mean, that goes especially for use cases where you quickly run into either time or space problems in terms of having to store terabytes, gigabytes, petabytes, exabytes of memory, where simply main memory, never mind secondary storage, doesn't measure up. Same goes for runtime. And this is where PDSs, if you are willing to trade in accuracy versus these kind of metrics, really make sense.
Exactly. And this is it's becoming even more relevant because nowadays we have the rise of big data. So we need to store a lot of data, but we also want it real time. And now how can we do it?
I have an idea.
You have?
You use a GPU database.
Oh dear.
Anyway, let's not go there today.
Okay, how about
Start of commercial break already, Martin? Full disclosure, Martin works at Berkeley at a GPU database shop. Richard, if you're listening, the email address is sponsor@linuxinlaws.eu. But Martin will fill you in the details.
Like that.
Okay, sorry.
For you that and offer.
Okay, but enough of the end of commercial break, and please do continue.
So yeah, and also another use case is where you is the exact opposite. It's not about big data now, but you have very limited memory on some devices, like routers or maybe some IoT devices, and you have a very limited memory space for it. So you cannot store a bunch of data there. So you can compare things. Let's say if a member is present in a set, for example. So
and I guess also for some questions, you don't need the exact answer, right? You don't need to know if it was 1,523,000. You just care if it's 1 million or 100,000, right? That's kind of, yeah.
Exactly. We can, we can, if you want, we can already, we can talk maybe about Bloom filters, which are one of the simpler ones, but they're pretty cool and they have some really nice use cases. So it becomes a little bit more obvious to the audience.
By all means.
Excellent.
And just go right ahead. Yes.
Okay, so we can. There are 4 main families of probabilistic data structures: membership, cardinality, frequency, similarity. Membership, basically, it is asking, so is this member present in a set? That's all it does. Now, what would be and Bloom filter is one of the probabilistic data structures, maybe together with cuckoo filters and different variants of Bloom filters, and that are the most prominent in this family. So a Bloom filter can answer your question like, for example, in the financial vertical. Has this user paid from this location before? Or has this credit card been reported as stolen? So imagine how many transactions are done in the world every day, every minute, every second, with how many different card numbers. Every one of those, I'm assuming that every one of those transactions needs to be checked if that card has actually been reported as stolen. So if all of those things need to go to some main database, some relational database, first of all, if you want to imagine the size of that database where we store all those credit cards, then that database has to be shared between different payment processors in the world. It needs to be updated all the time.
In real time, okay. Essentially, right? Because you're tracking transactions.
Essentially.
Yes.
And then you also, on top of that, you even have the problem of storing those. So the problem of security, you need to actually store those credit card numbers so you can compare if this new credit card that just paid is a part of those numbers or not. So in this specific use case, Bloom filters are a perfect match, because you can populate one Bloom filter by adding. You can have your list of all the cards that have been reported as stolen. You take them, hash them, put them in the Bloom filter. And now, every time someone wants to check if a card number is a part, it has been stolen, it just takes that number, hashes it, and compares it to what we have in the Bloom filter. The Bloom filter can give you two responses, yes or no. If it gives you the response no, it's that you can definitely trust that response. That means that card has definitely not been stolen. If it gives you a response yes, it means that, okay, this might have been stolen, but maybe not. If we go back to the shadows analogy here, it can say, okay, well, you are asking, okay, is this ball present in the set? And then the filter looks and finds a shadow that looks like ball and say, yeah, I see a shadow of a ball. I think it is. I think it is present, but actually it was not a ball. It was a lamp, or it was someone's head,
or a head or something. Exactly.
Exactly. But it cannot find any shape that looks like a ball. It can definitely say no, for sure. There is no balls in this set.
So no false negatives. If you throw a triangle at this set, it will definitely say sorry, not present.
Exactly. So in this case, for this specific use case, when you're checking if a card has been stolen, the most valuable response to you is no, because in most of the cases, in most of the transactions that you're going to make, the response is going to be no, right?
Okay.
And just by knowing that for sure, if your Bloom filter answers no, that prevents you from having to go to the main database to check. So we save a lot of load on the main database somewhere, or at least some relational database.
Another use case would be Netflix, right? Netflix, it's one of these hipster video networks, yes.
Yeah.
Because Netflix uses caches all over the place, funny enough. And if I understand this correctly, essentially what Netflix does in that particular context, they store chunks of video information in local caches. So if an endpoint, like a mobile device or a browser, basically goes back to the middle tier asking, hey, I need this chunk of video, is it present in your cache? Mm-hmm. All you have to do is basically apply a Bloom filter, and if it's not present, you simply go upstream and get it. But otherwise, you can basically directly stream it from the cache. Exactly.
Yeah.
I have a question, Elena. How would that lookup compare to, say, an index lookup on a radix tree in terms of time cost?
It's all one, if I remember correctly.
Because you just have to compute the hash function, right?
Exactly, because it doesn't depend on anything. You just need to compute exactly the hash function, and not just that, the memory needed to store all of to store the Bloom filter versus all of the cards that have been stolen in a full a string or a number or whatever it is,
Sure.
is very big. And imagine then if you also need this then propagates even further, because your full data structure containing all of the stolen cards, if it's 2 megabytes or 200 gigabytes, and you need to sync that between regions, so everyone can have a good latency, it really does make a huge difference, right?
Makes sense, Martin?
Yes, of course. Yeah, sorry. It's a lot of stolen cards, but hey.
Martin apparently is,
I'm not sure I want to be using credit cards anymore.
Martin apparently is pondering the possibility of going into credit card fraud wholesale. Excellent, Martin. Keep it going.
Got to know the variables here.
Sorry, this is proprietary, I'm afraid. Okay, very, very interesting and useful information there, and especially with regards to use case, because fraud detection is becoming much more of a problem than, say, 10, 15, 20 years ago because of the rapid move into online business. Never mind Heineken, Carlsberg, or what is the other third beer there? Corona, sorry, yes. Corona or not. So more and more people are buying stuff online, and needless to say, most of the time they would use some sort of credit card, debit card payment method. And so fraud detection is becoming more and more important as we speak at this very point in time, because needless to say, if you're a merchant, if you're a credit card processing company, you want to make sure that you are not being ripped off. Goes without saying.
Yes, exactly. And there are many other use cases. Mostly, I think it's the better fit when the meaningful answer to your question is no. So whatever is going to prevent you from going, if you get a yes from the Bloom filter, that's still okay. You just know that, okay, well, in this case, I'm going to go and have to ping the main database, whatever that means. But all those no's, all those no answers prevented you from going to the main database all the time.
Just curious,
much better latency, of course.
Yeah. Just curious, Elena, because this whole thing rides on the hashing function, but what would be the typical probabilities, let's put it this way, of your average PDS implementation, let's put it this way, with regards to accuracy? As I said, I reckon at the end of the day, it depends on the implementation of the hashing function. But what is your experience with regards to the probabilities coming back that you have experienced so far? If you can talk about this.
Yeah, of course. That should be totally configurable. Everyone can implement their own Bloom filter. That's really not a problem. The algorithm is out there. People can do it, and the accuracy is going to depend on the number of hash functions you're going to use, which is of course then gonna influence the CPU usage, right? And the size of your Bloom filter. So the bigger the bit array, the more precise, the more accurate filter you have. The smaller the bit array.
Yeah, we should probably explain why a bit array now comes into the context.
Bit array is then the field, the canvas on which we are projecting the shadows. If our canvas is 1 by 1 meter and we are projecting 20 shadows on that 1 by 1 meter, it's going to get blurry, and after a while, you're not going to be able to recognize anything. Everything is going to look like everything. If you're projecting the same 20 elements on a 10 by 10 canvas, they're going to be much more spaced out, and you're going to be able to recognize them much more nicely.
Okay.
Yeah, I was just to make the point clear. The size of the bit array in this analogy is the size of the canvas.
Okay. You alluded to the whole thing earlier on, but why are they called Bloom filters, and why is Bloom that much of a mystery?
For me, I don't know why he chose, or if he ever chose to be a mystery. For me, he's a mystery because I couldn't find anything about him on Google.
He's the chap who invented essentially the algorithm behind this.
Yeah. I think in the 70s or something like that. First, it was used for a dictionary, actually, to check words against the dictionary.
Yeah.
But
Full
yes, that's
detail.
Mr. Bloom.
Full details, of course, including the quantum imposition of the Bloom filter, will of course be in the show notes. But do carry on, Elena.
Well, that's it. I don't have anything else about the mysterious Howard Bloom.
Howard Bloom, okay. But is he still alive, or is he?
I don't know.
Nobody knows. Okay.
When I was researching that last year or a year and a half ago, I couldn't find out anything.
But he's not Irish, is he? Yeah, but he's not Irish.
I don't know.
He's not Irish, perchance, is he? No, I'm just wondering. That's all.
I don't know. Maybe even I don't know if I ever knew that, actually. I don't know if I could find that.
On the off chance,
which university he worked.
Yeah, on the off chance, Mr. Bloom, if you're listening, the email address is feedback@linuxinlaws.eu. Please get in touch so we can plan you in for an episode coming along in the future. Okay, going back to the corresponding Redis implementation now. The way I see it essentially is that there are a couple of implementations of Bloom filters in Redis. Maybe you can elaborate on these.
We have one implementation of Bloom filters, although we do have something quite specific to us. I don't know if it's patented, but one of the people who worked, Ariel and Dr. Carlos Vaquero, who worked on that, they released a paper. It's a scalable Bloom filters. With these scalable Bloom filters, you could just specify an error rate you want to keep. So you would say, okay, I want my error rate to always stay below this value. And then as you add more elements to the Bloom filter, it's going to just scale up. It's going to keep stacking filters one on top of the other. And so it can keep your error rate to what you requested. So that's pretty specific to Redis Labs, to the Redis Bloom implementation. But just to go one step back, first of all, the Redis Bloom module is the module that for Redis. Redis implements a module API where anyone can go ahead and create a module in C and extend the data structures.
Elena, sorry, what's a module? Please be more specific.
Exactly.
So that people understand.
Module, it's a piece of code written in C that uses the Redis API, the Redis module API, and then you can use Redis basically, and you can also hijack even some commands that are sent to the Redis server. So you load your Redis server with your module, and you can get you can implement your own data structures. So in Redis, you have you have strings, you have hashes, lists, you have a few data structures. With the Redis module, you can implement your own. And in the case of the Redis Bloom module, we have 4 new data structures that were implemented through that module. It's the Bloom filters, the Cuckoo filter, which is similar to Bloom, but implemented quite differently, let's say, but similar use case. It's from the membership family. We have the count, min, sketch, and the top K heavy keeper. Those are the 4 data structures that we have.
You mentioned that there were 4. The 4 different types have different purposes. So I think so. Bloom filters are membership orientated. What are the others for?
Yes. So cardinality, that is another family. Cardinality is to estimate the cardinality of the set. So membership is to determine if a member is present in a set. Now, cardinality determines the cardinality of a set. Frequency, obviously, the frequency of elements in a stream, and similarity to determine how the grade of similarity between elements, but non-deterministic.
Okay.
When would you use the other ones?
When would you use?
Have you some examples?
Okay, so for cardinality, in the Redis Bloom module, we don't have anything for cardinality, but we have the hyperlog log, which is a native Redis data structure. And we can talk a little bit about that because it's another super cool one. With the hyperlog log, in only 12 kilobytes of memory, you can estimate cardinality of huge sets. Let's explain that with a use case. So let's go with the YouTube video, for example. Okay, so in YouTube videos, you have a number of views, right? With these views, how would that work conceptually? Well, let's go with IP addresses or whatever kind of unique user identifier we have. Maybe user ID, maybe some combination of some IP with whatever identifier, browser, whatever, cookie or something. So you have any kind of unique user ID. And then every time that user ID views a video, you need to decide if that user has viewed that video before.
Okay.
Yeah. So in order for you to be able to do that, you need to think, well, how can I know if they viewed this video before, unless I have a list of everyone who's ever viewed this video before. And then I compare to that list, and then I know. The more viewers I have, the longer this list becomes. It becomes pretty much unmaintainable in years. What happens with the hyperlog log? Every time you have a new user coming, you get its ID, you just stick it in the hyperlog log dataset, and then every time you query, you ask you query that the data structure, say, okay, how many unique elements do you have inside, and it's going to tell you. And no matter, you can add huge numbers. At the moment, unfortunately, I don't remember the numbers. The still guarantee low errors. I think the margin of error was 0.1%. But it's going to tell you, okay, I've seen this many unique elements. And it's very interesting how it's implemented inside, but I think I'm not sure I will be able to explain it very well with just words and not visual explanation.
No, that makes sense. I think I think we're going to need this for the listeners to our podcast as well. Yeah,
the details, of course, will be in the show notes.
to keep track of all of them.
There is actually, I do have a presentation I gave on UbuntuCon, where I explained, I have a few minutes explaining how the hyperlog log works internally. Maybe you can link that if someone's interested.
Yes, the details, of course, will be in the show notes, dear listeners.
Okay, so that's about the cardinality family. The frequency family estimates with what frequency some elements occurs in a set without having to store all the elements that have ever occurred in that set. And in the Redis domain, we have the count min sketch and the top K in its heavy keeper variant that work with that. And the top K is the more performant one. What it does is, okay, you watch all the elements that show up in some stream, and you can see what are the elements that appear the most, the top 5, top 10, what are the elements that appear most. And this can be a nice use case for this. Can be maybe in gaming, what are the key players with highest score? If it doesn't matter if you can sacrifice some precision, and you have the flow is the incoming game score. And then you can even store a separate sorted set storing the top K users. Every time a user scores points, it's added to the top K list. Or then trending hashtags. So for social media platforms, so new distribution networks, you can say, what are the K hashtags people have mentioned the most in the last X hours? Yeah, and then imagine how the flow of information, how many hashtags someone would have to store. But if you post every hashtag, if you pass every new post and every new hashtag through this top K heavy keeper, then the top K is going to actually store and give you the top K hashtags that have appeared.
No, I think what is important in this context is actually the observation that all these hashing algorithms, all these probabilistic data structures rather, are scalable. because essentially what they just saw are hashes. So never mind whether you throw 10K values at them or a petabyte of data, the data and CPU cycle consumption is predictable to some extent. This is a property you do not necessarily have with ordinary data structures. And the sets and the sorted sets that Elena just mentioned are probably the two primary examples here. And sorted sets are not just a Redis internal data structure, but is essentially a set that where each and every element has a score attached to it. Think of it like a leadership board or a recommendation list. It gives you a sequence of the elements in a set, just for the few listeners who do not know what a sorted set is. Okay.
So,
sorry, go ahead, Martin.
Yeah, I was going to ask, so does this one have a error rate attached to it as well?
The top K? Yeah, yeah, it does. It's an estimation, because there's also, with the top K, there's also a decay algorithm where it, so the top K, it's not the top K since the top K was instantiated. It's the heavy hitters in the last whatever time, there is a decay algorithm. At the moment, I don't remember how exactly it was working. I would have to read my own article to remind myself, because it's been over half a year that I haven't checked. But the analogy that I had for this is, imagine, so they call it elephant flows with the heavy hitters. If you
elephant, did you say? Oh.
Yeah, elephant flow, okay.
So if you have a field, and then you have 5 elephants elephants passing through it, one behind the other, they're going to leave some trail. Yeah.
Yes.
But then you have 10 elephants going in another way, they're going to leave another trail. And then maybe you have a whole herd that goes on an opposite direction. And then after they're gone, what you're going to see, the tracks you're going to see in the field is mostly the one from the full herd. The ones from the 5 elements and 10 elephants, the ones from the 5 elephants or 10 elephants are going to be mostly deleted, and they're not going to be visible anymore because of the full herd that passed there. So it's not that much time related as in the volume related. But then after a while, wind blows, you have sandstorms or any kind of storms, and even that track of the whole herd starts to fade out and newer tracks start to form. Top K can be visualized like that for the people who like to visualize things.
And Elena, you mentioned that there are actually 2 types of PDSs called filters, namely the Bloom one and the Cuckoo one in Redis. Maybe you can shed some light on the commonalities and the differences.
Yeah, well, the Cuckoo filters, and they also check, and they enable you to check if an element is present in a set, and also using a very small memory space, fixed size, they sacrifice some precision for it. But they're implemented completely differently. For some cases, they are maybe faster for checking, but not faster for adding elements in the filter. There are some particularity, but the biggest difference here is that the Cuckoo filter, from a Cuckoo filter, you can delete elements. You cannot delete elements from the Bloom filter. So that is one big difference. The second difference, then maybe more subtle, is for Cuckoo filters, you only get discrete error rates that you can set. So maybe 0.4 or 0.7, depending on the implementation. But specifically for the implementation in the Redis Bloom modules, you cannot choose any rate you want. You have a set of discrete error rates that you can choose from. Another thing is that even though it's maybe faster for some use cases, if you repeat, it's going to fill up faster if you add the same element to it twice. So in Bloom filters, if you add the same element for a second, third, nth time in the Bloom filter is not going to change. Nothing's going to change inside of it. With the cuckoo filter, it will, and you're going to end up with that element twice or 3 times.
Okay. I assume all the implementations of these modules are open sourced. Is it available on GitHub?
If they're not, I think they're source available license, not open source, in the Redis Bloom module. But the difference is there. I don't want to go into that discussion.
Well, what matters most,
with you, Chris.
yeah.
But I don't know if you've ever talked about the source available license.
No, I haven't, and there's a reason for that. And this is not a licensing podcast, but rather, full disclosure, actually, there will be an upcoming episode on open source licenses. Summertime frame, so stay tuned, people. If you're interested in open source licenses, or if you can't get to sleep at night, just a hint, just don't miss this podcast. But this is not something that we will go into tonight. The main point is actually that all the source code is available on GitHub of this implementation. Whether the use case, of course, it may be a different one, but if you want to take a look at how it's done internally as an implemented, feel free. Yes. And I think, speaking of modules, the main implementation language is still C, right? But I think there's one module implemented, I think, in Rust these days, and it's Redis JSON 2, if I'm not completely mistaken.
Yes, I heard so.
Okay.
Has this been released now? Or?
Yes, it has, and I think some people use it already in production. This is, of course, a shameless plug for Rust, but let's not go there. Full disclosure: yes, there will be a podcast episode of the Linux Inlaws on Rust, but this is now enough with the commercial breaks. Let's continue with the PDSs. Okay, Martin, any I wouldn't say final thoughts, but any thoughts on any questions on PDSs?
Well, I'd like to go back to Eleanor's opening statement that there were 4 different types. Have we covered all of them?
We gave an example for membership, cardinality, frequency. We didn't give any membership for similarity. I don't know any implementation personally. That's why I don't want to go there. But similarity, in general, it can estimate how similar or different 2 elements are in a set.
Okay. So are you familiar with the roadmap for Redis Bloom, perhaps? If I mean, it's been around for, I don't know, a couple of years at least, in its final current form. But,
I think that was pretty stable. I haven't seen any big developments in there.
Full disclosure, D-Wave got in touch with regards to quantum hashing integration of this, but I'm not too sure what the current status is. Better check with product management. Full disclosure, people, that was a joke.
Quantum hashing. Cool.
An active area of research, if I understand this correctly, and Martin, beyond the GPU database field, I'm afraid. Okay. Last question, basically, that I have, because this whole thing, although it sounds very theoretically minded in terms of the math behind all the rest of it, but Netflix and friends must be just the tip of the iceberg. I reckon from a practical use case perspective, the applications must be a multitude of algorithms basically making use of this.
I think so. And I don't know if we can talk about what I've seen in Redis Labs, but there are people, we just touched on a few use cases, but imagine let's say a Google sign-up form. Every time you try to create a new Google address, it has to check if that your email already exists. There you have it, another use case for a Bloom filter. Has this email address been used already? Or a dictionary. So is this word that I just wrote in the dictionary, is it correctly spelled? And that was actually one of the primary use cases for the Bloom filter.
Which is quite understandable because, as we all know, languages can be complex beasts.
Yeah.
Even our languages outside the programming languages realm.
Yeah. I mean, the correct spelling, at least a very basic way to highlight a word that doesn't exist in the dictionary. You can look at it like that.
Cool. Sounds like a very good use case indeed.
Any final thoughts before we go into the epoxes and the anti-epoxies?
No, I just about the probabilistic data structure realm. Once you get to learn what they can do, you really kind of start to fall in love with them. You start to see applications everywhere, and it's good. It's a very good tool to have in your developer tool belt.
By the way, Elena, where do you see this going? I mean, I'm not talking about D-Waves now. I'm just talking about kind of from an application perspective, maybe from an implementation perspective.
This in terms of what? Of the development of the Redis Bloom module?
Anything goes.
Where the humanity is going, for example, to Mars.
Or whether the cartels will flip the coin in terms of fraud detection. You never know. No, I'm joking, Elena. But if they had kind of visionary thoughts, now is the time.
Well, if the direction is more and more data and more real-time requirements, then I think that we are going to see many more new algorithms for probabilistic data structures. We're going to see new implementations that we haven't thought possible, and probably even more uses for the current algorithms and improvements. Even the Bloom filter algorithm has already been improved multiple times. There are multiple variants of it.
I mean, this is the beauty about math, right? Similar to computer science, it never sleeps. because people are basically just wondering what is wrong with the current state of things, take it apart, put it back together again, and improve it.
Engineers.
Funny enough, this is the very core thought of something called open source, if I'm not completely mistaken.
Can we get some of those engineers on Jitsi, perhaps?
Jitsi, if you're listening, please get in touch.
Hey, come on, it was good. It worked well.
Yeah, it didn't break down this time, yes, but we probably have to cut this out. Okay, guys, that has been a very fun episode. Never mind missing math, but we don't want to bore our listenership rather to death. So this was actually very light on math. Needless to say, there is a complex mathematical foundation of this beyond hashes. Details, of course, are in the show notes.
Probably be tricky to do on a podcast too.
Yes, exactly. And with that thought, I think it's now, as the tradition demands it, now's the time to go into the epoxies. Elena, I'm not sure if you're familiar with the concept. The epoxies are the picks of the week. This acronym is actually trademarked by Linux Inlaws. So anybody trying to rip this off, our lawyers will be in touch. Jokes aside, anything goes. Anything that crossed your mind worth mentioning, Elena, in terms of font remembering, something that you really liked that has crossed your path in, say, a week or two or something, and then we take turns.
It's what? Can you say it again? What is Foxy?
Yes. Anything that you fancied, anything that came across positive.
No, but what? Positives of okay.
Yeah, I mean, we normally confine ourselves to movies these days. But anything goes. Can be a movie, can be a TV series, can be a music, can be a book. You name it.
Hey, you know what? It was a sunset. I hadn't went out. I'm in Portugal and we have been in lockdown for a while, and it's crazy how this. But after a few weeks of not going out for walks in nature at all, We finally went out for a walk in the sun. And it was finally also a sunny day after many weeks of rain. And it was weird. I just felt that I sprung right back to life. And I realized how much the sun and being out in nature makes a really big difference in our lives.
Certainly a valid point.
Sorry, not technical at all.
No, that's fine. Anything goes. As a matter of fact,
does that make rain your antipox?
We cover that in a minute, Martin. Okay, full disclosure, I had the very same experience today as Elena, because I took literally an hour-long break, actually done some cycling in Frankfurt. It was about 15 degrees, but the sun was shining. And that was, in the current situation, Germany is still under lockdown. Yes, a welcome diversion. But over to you, Martin.
I think, well, after today, I think my POX of the week is probabilistic data structures, because it's a while since I used Redis, but it's a beautiful piece of I guess algorithm for most of these. Yeah.
Okay. Antipoxes, if there are any.
I'm going with rain. I'm going with rain.
Great minds think alike, because I was just about to say the weather forecast, because the weather forecast predicts actually return of winter come tomorrow for central Frankfurt, where I'm living. So,
nice.
Okay, fair enough. Elena, any thoughts on a possible antipox?
Puppies. Sorry.
Say again?
Puppies. Everyone loves
puppies. Okay, you probably have to explain why.
The flowers or the dogs?
Really? No, the dogs, the baby dogs, puppies. I don't know if I want to explain exactly why. It might be too much information.
I take it you don't have a dog then.
You still have only one, right?
Yeah.
Okay. We will probably leave it at that. Okay. Guys, or rather, Elena, that has been really fun. Well, thank you very much for joining this. Hope to have you back. More than welcome to. We hope to have you back, or Olga for that matter, in an upcoming episode very soon, and really looking forward to it.
Thank you, guys.
Yeah, thanks so much, Alan.
Thank you. This is the Linux Inlaws.
You come for the knowledge,
but stay for the madness.
Thank you for listening.
This podcast is licensed under the latest version of the Creative Commons license, type Attribution Share Alike. Credits for the intro music go to Blue Sea Roosters for their song Solid Market, to Twin Flames for their piece called The Flow, used for the segment intros, and finally to Celestial Ground for their song Sweet Justice, used by the Dark Side. You find these and other ditties licensed under CC at Jamendo, a website dedicated to liberate the music industry from choking copyright legislation and other crap concepts.
You've been listening to Hacker Public Radio at hackerpublicradio.org. We are a community podcast network that releases shows every weekday, Monday through Friday. Today's show, like all our shows, was contributed by an HPR listener like yourself. If you ever thought of recording a podcast, then click on our contribute link to find out how easy it really is. Hacker Public Radio was founded by the Digital Dog Pound and the Infonomicon Computer Club and is part of the binary revolution at binrev.com. If you have comments on today's show, please email the host directly, leave a comment on the website, or record a follow-up episode yourself. Unless otherwise stated, today's show is released under a Creative Commons Attribution Share Alike 3.0 license.